those are the formulas that we will get to use. All right, so along the y direction, it's the same as free fall. Along the x direction, it's uniform motion, with zero acceleration. A project done by a Chicago student. Evidently, students saw this good-looking girl, woman, walking around in Chicago. There was a pigeon in front of her. So instead of walking around the pigeon, she kicks the pigeon. Motion that you're looking at is projectile motion. The only reason why you end up getting a parabola is because the acceleration along the y direction is constant, it's fixed by gravity, and there's absolutely no acceleration along the x direction. There's zero acceleration along the x direction. As a result, you end up getting a perfect parabola. So what do we know? There's going to be a zero uniform acceleration along the x direction. There's no change in speed. All right. So notice that if you know the time, you know the location along the x direction, and there's not going to be any change in speed. So your initial and final speeds along the x direction will be the same. All right, so we got 5 equations. All right, guys, put your answers in the chat. Okay, so I see a lot of A, so A is the best answer. So acceleration is going to be constant. Along the x direction, it's going to be constant at 0. Along the y direction, it's going to be constant in roughly about 10. So either direction, the acceleration is uniform. So this is an example of uniformly accelerated motion. Give yourselves 5 points. A further demonstration that free fall and projectile motion are the same. Along the y direction, they accelerate at the same rate. They will slow down at a constant rate, going up against gravity, and they will speed up at a constant rate, going in the direction of gravity. In the projectile motion, this also has horizontal speed. Side-based projectile motion is what we're focusing on.
If you're in Mexico and you can't decide between the bullfights or cliff diving, we've got the perfect
I got 2 examples of side-based projectile motion coming up.
town for you.
This is the first one. This one is the second one. So the side-based projectile motion, there's going to be a horizontal speed, and there's no vertical initial speed. All right, so example, the problem one is going to be related to this mind twister that we started the lecture out with. He drops a bullet, she fires a bullet from the same height, and both of them will land at the same time. Okay, so at least we've seen the experimental evidence that this is correct. Came up with the mathematical model. Now we're going to test our model against the experiment. So this is problem number 1. All right, so this is number 1 from the handout. Okay, one of the things that I want you to get used to is when necessary, just draw things out. Okay, so it's going to make thinking so much easier. All right, so there's going to be an initial speed on the x direction. I'll get you the numbers. All right, so the bullet is going to be fired. This is the amount of time it takes for this bullet to drop. So that's the same amount of time it's going to take for it to travel this distance. This is going to be fired at 2,500 miles per hour from 6 feet above the ground. Gravity is the only force acting on it. So it's going to cause a constant acceleration. Roughly, I'm wiggling at 10 meters per second squared. You can use 9.8 if that's what you want to use. All right, so how long does it take for it to actually fall? That's what I want to know. All right, so obviously we have to do the conversion, so miles per hour to meters per second, 50 meters. All right, so I get my conversions done. All right, so everything is converted. Okay, now we have to do a little bit of work for a change. Okay, so let me just list all the 5 formulas that we got. And then I'm just going to label them, so we got 5 formulas. Okay, now we got to make a decision. Okay, so in terms of making a decision, okay, so this is going to be slightly more complicated than what we were doing last week, because this is going to involve a little bit of thinking. All right, so what are you looking for? You're looking for T. All right, so first thing you have to do is, these are all the symbols available to you up to this point. So X is not available to you for this section of the problem. So focus on the formulas that have T in them. Right, the first one has T in it, the second one has T in it, the fourth one has T in it. Okay, I'm going to start off with the very last one. Is there any way we can use the last one in order to solve for T? All right, so we know the initial speed, but we don't know the distance that it travels along the X direction. So we got 2 unknowns here. If you have 2 unknowns, you cannot use it. Okay, this is not a wise approach to solving this problem. So 4 is out of the question, so we're not going to be able to use 4. All right, so you cannot use 4 for this one. 4 is not going to work. So those are the 4 symbols available. All right, so 4 is not going to work. Okay, so how about the second one? Can we use the second one? We got P here, but we don't have the final speed on the y direction. This speed is not available. So the second one is out of the question. The only one that we can use is the first one. P is what you're looking for. G is known. Also, the letter Y is known. So we got one unknown. Right, so fourth one is out of the question. The second one is out of the question. The only one that you can use is the first one. All right. Just say you have to do trial and error for this one. Right, so move on to algebra and isolate T. Once again, guys, I will keep saying that, and eventually through pain, you'll notice that I mean business. You're not allowed to use numbers when you do your algebra. Okay, so you will have to use symbols when you do your algebra. It's cleaner and it's easier to grade, and just get used to it. All right, so get rid of 2 and get rid of G, get rid of the square, and we're done. That's it. Okay, now you got a number for G and you got a number for the letter Y in terms of the metric unit. So just plug those numbers in and carry out the number crunching. So you end up getting 0.6 of a second. So what that means is this bullet, after it's fired, is going to take 0.6 of a second to reach the ground. So the next question is, how far does it travel? Is it dropping down? So X is what we are looking for. And lucky for us, there's only one single formula that has X in it. So that's going to give us the distance. So now we know the time is going to be 0.6 of a second. We also know the initial speed, which is this huge number. So get the formula. Okay, so there's not much to do there. That's your algebra, just a single equation. And plug the numbers in. It's going to give us a number in terms of meters. Okay, so this number is not going to make sense to anyone. So what we need to do is we need to convert it to something we can all relate to. That's a big distance, guys. 6, that's like more than half a kilometer. For those of you guys who know what it is. So it's best to express it in terms of miles. Only to realize that this is going to be 0.4 of a mile. Okay, so now it kind of makes sense. What that means is, by the time this bullet reaches the ground, which is going to be a fraction of a second, 0.6 of a second, it's going to travel 0.4 of a mile. That's almost half a mile. All right, so that from a rifle, that's actually to be expected. That's not surprising. So the next question is second bullet, one that you drop. How long would that take? Well, it should also take 0.6 of a second. So let's check to see if we can get that. Remember, this is free fall. So what do we know? We know that it's going to be following the same distance. All right, so the distance is going to be the 6 feet. So you know the distance, you know G, you have to figure out T. So that's equation number 1 is the only one that you can use. In essence, we used that previously in part A of this problem, guys. A and C are identical. It's going to give you 0.6 of a second. So our mathematical model also works just fine. In mathematics, the model that we came up with works. It agrees with our observations. All right, so put down your responses in the chat. Okay, good, guys. If one of them takes 4 seconds, the other one is also going to take 4 seconds, right? If fire bullet and drop bullets will land at the same time, the one which is projected at 30 meters per second, if it takes 4 seconds for it to land, 60 meters per second is also going to take 4 seconds to land. Beautiful. Give yourself 5 points. All right, so now let's make a transition from projectile motion to impact. Okay, so projectile motion is going to end with impact. Impact could be soft, which means that you will have a really large acceleration time. Or it could be hard, which means that your impact time is going to be fairly small. Your acceleration time is going to be small.
Television cameras are on hand to capture a death-defying stunt. Daredevil Jean-Louis Arola is about to attempt a dangerous mid-air plunge into the frigid waters of the English Channel. A risky maneuver calls for him to drop from the plane as it speeds above the surface of the water. Jean-Louis carefully climbs out and secures himself to the belly of the fuselage. The aircraft approaches the drop zone.
Okay, so we got some problems here. Let's say 30 feet drop, and he's a stuntman, which means that this guy actually does this sort of stuff for movies. And when they shoot these scenes, and today mostly they do special effects, but if they have to get a stuntman to do something like that, they would get a physicist to do the computations for it, just to make sure that no one is getting hurt. All right, so from the looks of it, someone missed the point. I think they end up focusing too much of the distance fallen and less on the fact that the airplane was moving horizontally. And this doesn't look too good at this point. Okay, so the question is, whatever the impact that this guy underwent, question number 1, is that survivable? If it is, what's the damage? Okay, so let's do an analysis on this one. So what do we know? We know that the airplane was going at 80 miles per hour. And then when this guy jumped, he fell about 30 feet. That's it. That's all the information that you have. From that information, can you figure out whether or not the impact is survivable? Okay, guys, your test question next week is going to be like this. All right, so you're not going to have a lot of details. I'm going to give you the essentials. And out of that, you should be able to do a complete analysis. And how it is done is something that I will show you first. First thing I'm going to do, I'm going to step you through it so that you can see how the work is done. Next thing is, this is calc-based physics, which means that your problem-solving skills have to be a little bit more sophisticated and sort of problem-solving that we were using so far. All right, so what do we know? 80 miles per hour horizontally. That's how fast the airplane is moving. So when he jumps, he's already moving in the same direction at the same speed. Horizontal speed is going to remain the same all the way down. There's no reason for him to go any faster or slower. All right, once he's airborne. And while he's moving horizontally at speed, he's going to fall 30 feet. I'm going to draw this out. So he's moving 80 miles per hour horizontally as he's dropping in the y direction for about 30 feet under the influence of gravity. All right, and then he's going to land in water. All right, so let's figure out the vertical speed component of the final speed, y component. Figure out the horizontal component of the final speed. If you know the vertical and the horizontal components, now you can construct the final speed itself. All right, so figure out the total speed. And there's a bit of a shallow angle here, so figure out the angle of impact. And that's it. Okay, so that's our starting point. So figure out the final speed, and then we'll do an impact analysis. So I listed everything. Before I move forward, I just want to make sure that everything is in the correct form, because you don't want any confusions. You want to make sure that your numbers are in the proper form before you move forward, because this thing is going to be involved. So miles per hour to meters per second, feet to meters. Okay, guys, we've done the conversions quite a few times. At this point, it's a good time. This is chapter number 3. I know how to do the conversions. I haven't seen the first test yet, but at this point, I have to assume that you do know how to do it. All right. So moving forward, what do we do? Okay, so without showing the work, I do the conversions because I know how to do them, and you should too. So miles per hour in terms of meters per second, feet in terms of meters. Okay, we're good. So the next point is just find the y component of the motion. Speed, final speed. Immediately you notice that there's 2 formulas that you can use, 2 and 3. Both of them have the y component of the final speed. Now you've got to make a decision. Do you pick the second one or the third one? Well, try to pick the second one. Immediately you notice that you don't have time, so it's out of the question. So through elimination, trial and error, you know that the third one is the only one you can use. Okay, because you know the distance found. Okay, cool. Get rid of the square. I think the square root. That's as far as this goes. All right, so the numbers in terms of the metric units. And then obviously the number in terms of something that you can understand. So this is roughly about 30 miles per hour. So this guy, when he hit the water horizontally, the vertical speed was 30 miles per hour. Now, what is the horizontal speed? Horizontal speed doesn't change. Ignoring the effect of air friction, there's not going to be any change in speed. Okay, guys, horizontally, speed does not change. Right, that's it. Okay, so there's no reason for him to go any slower or faster. So horizontal speed is going to be 80 miles per hour. So that's the x component of the speed. So along the y direction, he's going at 30 miles per hour. Along the x direction, he's going at 80 miles per hour. So what is his total speed? All right, how do you get the total speed? It's obviously, it's called calculus, but I'm going to